Good morning, my YouTube viewers. It is Crystal here, and I'm here to give you another code review. And basically what we're going to be doing is we're going to be using TensorFlow, and we're going to be using it on the abalone dataset that actually is in TensorFlow. I think I've said this before in previous videos, but TensorFlow is more popular than sklearn, so it's important to learn TensorFlow, and that's why I am studying TensorFlow, so I can learn as much about TensorFlow as I possibly can. So this is the abalone dataset on TensorFlow, on the TensorFlow website. It's a TensorFlow dataset. So the first thing we want to do is we want to import our libraries. We're going to import pandas as PD, which is for data processing. We're going to import NumPy as NP, which is for numerical computations. We're going to import matplotlib.pyplot as PLT, which is for data visualization. And we're going to import Seaborn as SNS, which also is for data visualization. So to make NumPy values easier to read, np.set print options, position equals 3, suppress equals 2, true. We're going to import TensorFlow as TF, that's your deep learning library, and we're going to, from TensorFlow.Keras, we're going to import layers. So we're going to load the train data set, abalone train equals pd.readcsv, and then they give you the link for the train data set in the TensorFlow directory, and names equals length, diameter, height, whole weight, shucked weight, viscera, weight, shell weight, age, and you'll notice that all of these numbers are really low. Most of them are below 1, but some of them are above 1, but most of them are below 1. And then we check the info, and we can see that all of the columns or features are numeric. So that's good, because that means that you won't have to do any encoding. Check the shape of train as 3,320 rows by 8 columns, and the size is 26,560. So you just multiply the columns times the rows, and that tells you the size. We're going to describe it. So this is a description, and it gives you the mean, the standard deviation, the minimum, 25%, 50%, 75%, and the maximum. So the maximum whole weight is 2.82, so that's not very, those are not very large numbers. And now what we're going to do is we're going to read the test set, because I wanted to get the test set in there. And so we've got the test set, and then I'm just going to take this out. And then check info. You can see that it's all numeric, which is good. Check the shape, which is 850 rows by 8 columns, and the size is 6,800. And then we check the describe. So you can see all of the numbers are really low. Most of them are below 1. A few of them are above 1, but they're not very high numbers. So we're going to define the features. Let's just see. We're going to define features and label. So we're going to do a value counts on abalone train age. Value counts. We're going to see if there are any rows where you only have one occurrence of an age, and there are 3 rows where you have only one occurrence of the age. And basically what's going to happen is it's not going to do the prediction any good. The model's not going to be able to predict if you've only got one occurrence of a value. So what we're going to do is we're going to filter the data frame to filter out all of the ages where the value is above 1. And so now we've got 3317 rows by 8 columns, so there's 3 rows that it deleted, which isn't too bad. Okay, abalone features equals abalone train.copy. Abalone labels equals abalone features dot pop age. So pop is sort of like drop, but let's just see what it means. Let's just see what it means. The pop method removes the element at the specified position. So it's similar to drop. So I normally use drop, but they use pop. But I probably would have used drop, but they use pop. And I created a heat map, COR equals abalone features.core. And then we created a heat map of that. And so you can see that the length and the diameter are very close. But I decided not to do anything about it. I decided not to remove the columns that had a high correlation, just to keep them in there. So here's the correlation. So you can see that the length and the diameter is 98% or 99% really. So if I had decided to remove columns that had a high correlation, then the length or the diameter, or maybe even both, would have been removed. So because it's a small data set and the length and the diameter, in my opinion, are important, I didn't remove them. So abalone features equals NP array abalone features. So what that means is that you take the features and you convert them to a NumPy array. I guess that's what TensorFlow wants to see. We can do a question here. Why we can ask the question. Why do we convert data to a NumPy array? NumPy arrays are more compact than Python lists, which use less memory. NumPy is also not just more efficient, but convenient. There are a lot of vector and matrix operations in NumPy. There are also things built into NumPy, such as FFTs, convolution statistics, histograms, etc. So that's why they want to convert it to array, because it's more efficient. So now what we do is we create a histogram using Seaborn. And so we can see what the labels look like. And you can see that it's skewed as well. So now what we're going to do is we're going to define our model, which is going to be in Keras. It's going to be Keras sequential. So it's going to be layers.dense64, and then that's what the input's going to be going into. And then layers.dense1, that's going to be the output. And then so what we're going to do is we're going to compile it, and we're going to do the loss on mean squared error and the optimizer on Atom. So we have a loss of 4.7994, and how many did we have in here? We had 200. So we had 200 epochs. I set it up for 200 epochs. And so you had a loss of 4.7618. And then we do a summary. And then now we make our predictions. So prediction equals abalone model dot predict abalone test drop age axis equals 1. And you notice how I said drop. I don't normally say pop. What we can do a question here. So what's the difference? It says the pop function is used to return the removed element from the list. So it doesn't give you the difference between drop and pop, but it just says it's used to return the removed element from the list. But so I guess that means you can get it back if you want it, because I normally use drop. And prediction, we're going to filter the prediction out, so anything in the prediction that's less than 0 is going to be 0, and the prediction is going to be an integer. And so we've got all of our predictions. And then now we check our error. So our error is 2.3689. And then we check a data frame to check your actual versus your predicted value. And you can see that it's not making a really good job of it, but hey ho. Okay, so now what we do is we check our age. Well, what we do is we do use Matplotlib to make a visualization of the difference between the actual values against the predicted values, and you can see that there's some outliers in there. But what I might do, let's look over here. Now age definitely is an integer. Okay. Now we're going to do something called normalize, because there's a normalization in Keras Tensorflow. So we're going to do exactly what we did before, but we're going to normalize it. So normalize equals layers.normalization. And then we say normalize adapt abalone features. And then we're going to use the exact same model, except we're going to add normalize to it. So norm abalone model equals tf keras sequential normalize layers dense 64 layers dense 1. So 1 is your output layer because it has only one output. And then we're going to compile it with the loss is going to be mean squared error, and the optimizer is going to be atom. And then we're going to fit it and train it. And the loss is 4.8219 mean squared error. That's a model summary. Then we're going to predict on it. So we got our predictions, which is the same as the previous one. But we're going to check the RMS, root mean squared error. And that's 2.432. And you'll see that the root mean squared error when it wasn't normalized was 2.36. So the root mean squared error when it was normalized is more than the root mean squared error when it wasn't normalized. And then we're going to create a data frame so you can take your actual values and measure them against the predicted values. And then we're going to plot it on a graph, and you can see that there are quite a few, well, there are a few outliers. And so that's what we have done in this code. And in theory, the RMS should have been better when it was normalized, but it wasn't, it was worse. But I think that was because the values were really small anyway, and because the values were really small anyway, that affected the value. And it also says in the documentation, because I've got the documentation here, it tells you how to use the normalize. So this is the documentation that we're using. So it says only use your training data with preprocessing.adapt method. Do not use your validation or test data. So using this function, you're not supposed to use it on the validation or the test data either. So, I mean, me personally, what I would have done is I would have normalized it the way I normally do, which I'm going to do a blog post on that. But I wanted to show you how to do it on the way TensorFlow says to do it. But I would normalize it myself and then run the program or run the model without being normalized, because you can see right here that the RMS is less without normalization than it is with normalization. But I think that is because all of the values are really small anyway, and that's what I think. So I'm going to go ahead and conclude this code review. I hope you got something out of it. I look forward to making more code reviews for you. I would like to thank all of my subscribers for supporting my channel, and I will be communicating with you in the next video.